Okay, so last time we had finished off our transient analysis of a Miller inverting integrator. And what we saw was that we used a process which required us to convert the transfer function to the Laplace domain as well as the input to the Laplace domain. We performed the convolution, and then we essentially had to bring that function back from the Laplace domain to the time domain. We're going to move on now. We're going to essentially do the end of Chapter 2, which is sort of a grab bag of different topics related to op-amps. And then we should have some time to move on to Chapter 3 today and actually talk about semiconductors, which is really one of the first truly new topics that we're going to be discussing in this class, because op-amps was at least 25% review from circuit analysis. So before we move on to Chapter 3, a couple final things. So first thing is the differentiator op-amp. So last time we talked about the integrator op-amp. There's also the differentiator type. And so the differentiator type, as the name suggests, gives us the derivative of the input function. It's structured with the resistors and the capacitors in the opposite spots, a lot like how we adapt a low-pass filter to become a high-pass filter. We switch the locations of the resistor and the capacitor. And so it looks like this. We're not going to go into as much detail on the differentiator as we did for the integrator, but we are going to present the same basic expressions. So we have our transient description where the output is equal to a constant times the derivative of the input signal. And then we have a steady state AC description, which we will also call the transfer function, which we will also call the frequency response, where this is equal to negative j omega RFC1. As you can see, unlike the integrator, this op-amp presents a high-pass filter type behavior, where the gain gets larger as the frequency increases. So some basic characteristics of the differentiator type op-amp, right? The filtering characteristic is that similar to a high-pass filter. The magnitude of the transfer function is shown here, omega RFC1, and the phase of the transfer function is negative 90 degrees. Now, let's look at that for a second, because this is something that hopefully you should be able to pick out, but maybe is not completely obvious to everyone. So let's look at this transfer function right here, and let's explain, so why is the magnitude omega RC? So the way that we find this value is we need to do the conversion between the rectangular and the polar form. Another way of saying this is we could say this is equal to 0 minus j times omega RC. So the real part is 0 and the imaginary part is omega RC. Now, anytime we only have a real or an imaginary component, that is by default the magnitude, but you could also use the Pythagorean theorem, right? Square root of 0 squared plus omega RC squared gives us omega RC. So that is the magnitude, as shown here. Now the phase. For the phase, again, anytime you have a purely imaginary complex or vector, right? With no real component, it's either going to be positive 90 degrees or negative 90 degrees. This is minus, so we have negative 90 degrees. You could also use the inverse tangent in order to calculate that. So hopefully that makes sense to everyone and sort of sticks out. But if it doesn't, you want to make sure to take a look at something like that again. The differentiator time constant is the frequency at which unity gain occurs, and it's defined as 1 over RC. And then so, what's one problem with the differentiator? This is a problem that we often see for PID controllers when we use the derivative component. Does anybody know what that problem is? Well, it says it right there. Noise, right? So the derivative of noise can often be very high even if the noise itself is very small, because the derivative is just the slope. So even if we have noise with an amplitude of 10 microvolts, right? If that goes from negative 10 to positive 10 microvolts in a very short time period, a nanosecond, the slope of that is going to blow up, is going to be huge. So the derivative term of the PID controller often has limited applicability unless you can find some way to filter out or limit the range of the slopes that it's looking at, and that same problem would translate over to the differentiator op-amp. Okay, so the next part of the chapter 2 is that which I referred to in the beginning as sort of a grab bag of different imperfections associated with op-amps. We, up until this point, had largely been talking about ideal op-amps and relying on those ideal characteristics of an op-amp. Now we're going to take those away. So the first one that we're going to discuss is called offset voltage. So the easiest way of describing offset voltage is saying, right, when you have an amplifier and you short the input terminals together, what do you expect the output to be? 0, right? Output is equal to some gain times the input. If the input is 0, the output should be 0. However, that is, for a practical amplifier, often not the case. What happens is that even when we short the terminals together, we'll still get a small output. One way of imagining this is as shown in this picture here. So imagine that you have an ideal op-amp. This is ideal, the small blue triangle. It's inside of a larger non-ideal amplifier. So how would we represent offset voltage? We would represent offset voltage as a source in between the non-inverting terminal that you see and the actual non-inverting terminal. So what happens is when you short these two together, the actual input being supplied to the amp is this value VOS, which means you short these terminals together and you still have an output that would be present. Now, be aware that this is just a way of imagining the problem. There is no actual voltage source inside of the op-amp. So what causes VOS? Unavoidable mismatches in the differential input stage of the op-amp. It's impossible to match all the transistors perfectly, and in the input stage of the op-amp, the current takes different paths for that first stage. So, the range of VOS is normally, for, let's say, the types of amplifiers that we're going to use, somewhere in the range of 1 to 5 millivolts. And obviously, like high or low tolerance resistors, you can buy devices that offer lower or more accurate values, lower offset voltage values. Now, how do we determine what the effect of the offset voltage is on the output? Essentially, we multiply it by 1 over RF divided by R1. So this tells us for an offset voltage value and a closed loop configuration, this is the effect. Now, the one important thing, this works for both inverting and non-inverting type op-amps. However, this is with the assumption that the VOS is on the non-inverting terminal, which practically doesn't make any difference, but for some of the problems that the book presents, it does make a difference. So just be aware of that. So how can we reduce this offset? There's two terminals on an op-amp that we have not discussed yet. Those are called the offset nulling terminals. And so a variable resistor may be used to reduce the asymmetry present in the transistors and in turn reduce the offset. So what you do is you have these two terminals, you place a resistor between them, you calibrate it appropriately, and it reduces the offset. the question one may ask is, well, why don't they just do that in the factory before they give it to you? It needs to be individually calibrated and tuned to the device. So let's say you have a design with 20 amplifiers. You're going to have to pull each one out, short the terminals together, put your variable resistor in between the offset nulling terminals, and then play with it until you get a 0 output. And then put it back in the design, and so on and so on. And so it is a calibration process. And there's no guarantee that that calibration will be immune to drifting if time passes, temperature changes, or anything of that nature. So it is an improvement, but it's not necessarily a complete fix. And again, it would be dependent on the resolution of the resistors that you have available. So if you go down to the resolution of 10 ohms, you may get close. If you go to 1, you get closer, and then so on and so on. Another way to reduce this offset is to use capacitive coupling between the input of the amplifier and the amplifier itself, because essentially capacitive coupling, a series capacitor between the two, reduces any DC value. Now, this works well, but it has the downside of also removing the DC component of your signal. So if you're trying to amplify a DC signal, this is not a very viable solution. It only works if you're trying to amplify an AC signal with no DC offset component. Here you can see here, this is a figure from the book which shows the offset nulling terminals and the placement of a resistor in order to null that offset. And then here's an example of placing a coupling capacitor at the input of the op-amp. All right. Another imperfection that we're going to talk about is bias current. So we know ideally that the current absorbed or consumed by the inverting and non-inverting terminals of the op-amp should be 0. Is that actually the case? No. So the amount of current that's consumed here is referred to as the bias current, and then the difference between the two is referred to as the input offset current. So you sort of have two levels of imperfection. You have the bias current, which ideally should be 0, and then you have the offset current, which ideally should be 0, meaning that the two biases are equal to one another. So these equations here describe the relationships between those. The input bias current is the average of the biases at the number 1 and number 2 terminals, or the inverting and the non-inverting terminals. The offset current is the difference between them, and then similar to what we had 3 slides back, this represents the effect of the bias current on the output. Now, in this end of the chapter, when I say that I mean the end section of chapter number 2, there are fewer derivation-based problems, fewer long problems, right? It's mostly a matter of understanding these imperfections, what they mean. They could show up in the oral part of the quiz that we're going to be doing at some point. And also, for the midterm exam itself, just understanding what these equations mean, being able to find them in the cheat sheet and apply them properly. What I would say is, if you understand what the offset voltage is, solving that problem when presented to you should be pretty easy. The problem comes when you don't even know what offset voltage is to begin with, and you don't know what equation to look for on your cheat sheet. Now, how can we reduce the effect of the bias current? We can do that by placing a resistor R3 between the non-inverting terminal and ground. If you remember, for both the inverting and non-inverting configurations, there's no resistance between the inverting terminal and ground. So this R3 value we can place there, and it should be defined as the parallel combo of R1 and R2, or R1 and RF. And so that reduces the effect of the bias current. Another imperfection that we have to be concerned with is frequency dependence. So if you remember, two of the ideal characteristics of an op-amp were, number one, that the open loop gain is ideally infinite, And number 2 is that the bandwidth was also infinite, meaning that the open loop gain stayed constant from very small DC frequencies all the way up to very high, let's say RF base, relevant frequencies. That's not the case. So for an actual amplifier, we will find that the bandwidth is finite and that the gain will decrease with frequency. It exhibits a low-pass type behavior, often with a drop-off or a corner frequency as low as 10 hertz. Now, obviously, this depends on the application. For an amplifier that is designed specifically for communications, that value will be different. So what we see is that the open loop gain of the amplifier inherently has this low-pass type of behavior to it. So some terminology that we have to be familiar with. Internal compensation is essentially what we call the capacitive elements at the input of the amplifier, which cause this low-pass behavior. It's similar to the example that we did in Chapter 1, if you remember, where we analyzed the model representation of an op-amp where we had a capacitor and a resistor in parallel at the input. That would be an example of internal compensation. Frequency compensation is the process of modifying the open loop gain to improve or grow the bandwidth and increase stability. So we're not going to talk about the process of frequency compensation in this class, but you should be aware of what that process is. You have an amplifier with a low-pass type behavior where the gain drops off relatively quickly. You want to use that for an application where higher frequencies are going to be processed, and so there is a method to pushing this to the right. Here what we have are some transfer functions for the internally compensated op-amp. Essentially what this does is this gives us a more detailed look at what the open loop gain is actually going to be. Before, when we were considering an ideal op-amp, A was always infinity and was constant. In reality, A will be equal to some DC value divided by 1 over j omega divided by omega b. Okay? And so this is similar to the form that we saw for the low-pass filter, where omega b is our corner frequency, or our negative 3 dB frequency. So we have transfer function in the Laplace domain, transfer function in the frequency domain, which is just replacing the s with the j omega. We have the transfer function for higher frequencies. So when we're at high frequencies, this will be much larger than 1, which means that 1 is not so important, so we can approximate it here. The magnitude gain for high frequencies is shown, and then the unity gain. What is the unity gain? The unity gain is the frequency at which the gain is equal to 1, hence unity. And all that they're saying here is that the gain at higher frequencies is proportional to the ratio of the unity gain over the frequency itself. So now, how can we take that transfer function and loop it into something that we had looked at before? It looks like there's a lot going on here in this slide, but there's actually, it's really a really simple substitution. So if you remember this equation, well, actually, let me ask you, does anyone remember what this equation represents, what it describes? Yes? Exactly, yes. So, right, if we have, and this one specifically, if you look at the numerator, you can see it's for an inverting. So for an inverting amplifier, when the open loop gain is not infinite, the closed loop gain is described by this function, and we plug in the value of A there. Now we can take that one step further, and in here we can plug in our transfer function, or our transfer function for A. So we could take this, the non-ideal value of A, and plug it into that expression, which now would tell us the effect of frequency on the closed loop gain. And so that's all that is shown right here. I'm not going to go through it step by step. It's just cleaning up some of the math. But right, we take the non-ideal open loop gain, we plug in the transfer function, and we end up with this. And so what it does is it says, okay, for the inverting op amp, the gain, closed loop gain, is equal to negative R2 over R1 over 1 plus j omega, 1 plus R2 over R1. All this is stuff that you know. And then lastly, omega t, which is our unity gain frequency. The frequency at which the magnitude of the gain is equal to 1. Now, this is just one version of the equation you can make. You can see that by changing around the math, you could also derive a version of this which was dependent on the corner frequency. So it would look slightly different. You could also define it in those terms. Just note that there's some terminology back and forth here. We use omega b and omega naught in the same as the same value, corner frequency or break frequency. They're the same thing. So there's two versions of this expression. We've been talking about the version for the inverting op amp. There is a similar version for the non-inverting op amp. The denominator stays exactly the same. The only change you have is the numerator, where now for the non-inverting op amp, now the numerator becomes 1 plus R2 over R1. All right, so some other non-ideal characteristics that you should be very familiar with: output voltage, saturation, right? We've all seen this practically when we've been working in the lab. If you have, we know that the output of the amplifier cannot exceed the rails or the VCC that is provided to it. So if we're running an amplifier at negative or positive and negative 15 volts, then we would expect the linear range to stop somewhere between 13 and 14 volts. So that's all that's saying right here, is that is a non-ideal characteristic of an op amp. Then we also have output current limit. So anyone who's ever burned out an amplifier before has experienced the effect of this, right? The amplifier cannot just supply some infinite amount of current. The transistors inside of it, the components inside of it, are not able to handle that kind of heat dissipation. So the value that the book gives, it says approximately, a lot of the instrumentation type amplifiers you'll see will give you about 20 milliamps. Really, the best way to get that value is just to look at the data sheet. It's one of the first characteristics you'll see is what's the rated I/O, what's the maximum I/O. But again, right, this all comes down to a heat issue. How much heat? More current means more heat, and how much heat is the amp able to take before it burns out. Okay, slew rate is an interesting one. This is one that we're probably a little bit less familiar with. So slew rate is the maximum rate of change that the op amp output can experience. So this picture does a good job of describing it. Imagine you have this op amp, which is a buffer, a voltage follower configuration, which means that ideally the output's just equal to the input. And we give it a step change that looks like this. So this is the input. Ideally, our output would look exactly the same. But we know that the amplifier is internally compensated, okay, which means that it will have some sort of a short transient response. So instead of being able to pop directly up to this value, whatever it is, there will be a slope here. So we call this slope the maximum rate of change that this amplifier output can experience. We call it the slew rate. And, right, so as long as your input has a slope that is less than the slew rate, you'll be fine. But when you get to higher frequency, faster changing signals, then it will be problematic. So why does slewing occur? And what does that mean, slewing? Slewing is just when the rate of change exceeds the slew rate, we begin to see this sort of dragging that goes on. So in short, the bandwidth of the op amp is limited, and so output at very high frequencies will be attenuated, and that's reflected in these figures here. So this is another really good picture. Let's say you are inputting a sine wave that's running at a frequency that's relatively high. So the slope at certain parts of the sine wave is exceeding the slew rate. What will you get as the output? You'll get this sort of bouncing behavior where the amplifier is constantly trying to catch up, but is not able to because it's just going slew rate, positive, slew rate, negative, slew rate, positive, negative. Okay, homework number 5. So that'll be due a week from today. Just be cognizant, right? We are coming up on our exam, which is 2 weeks from today. So this will probably be, if not the last homework, one of the last homeworks that'll be covered in the midterm. All right, so concluding this chapter 2, we talk about the basic structure of the amplifier. I'll leave this, you can take a look at this conclusion in more depth if you want to. I'm going to go through it relatively quickly. We talked about the basic structure of an amplifier, the ideal characteristics of an op amp, and talked about negative feedback. Can anybody real quick just remind me, because this is like a really good question to ask, again, in that oral part. Why do we use negative feedback? What is the point of using that? So ideally, what is our open loop gain? Infinity, like we've said 1,000 times. That's not very useful for us. So we use negative feedback. We connect the output to the inverting terminal in order to bring the gain down to a finite value, and that's more useful. So we spent a lot of this chapter talking about negative feedback, both about different configurations that employ negative feedback, summing amplifier, inverting, non-inverting. The integrator also utilizes negative feedback, the difference amplifier, instrumentation amplifier. And then we talked about how to look at a configuration that employs negative feedback and calculate the closed loop gain. Right? So let's say we are not familiar with a configuration. We know the steps in order to calculate that. That involves a virtual short and the assumption that the bias current is 0. Again, we talked about some different configurations, the difference amplifier. We spent a lot of time talking about the instrumentation amplifier, which is shown here. Don't forget about small things like the change that we made where we removed the ground from the first stage of the instrumentation amplifier in order to improve the common mode gain characteristic. So that was something we spent a lot of time talking about in this chapter as well, was the difference between differential input and common mode input, differential gain and common mode gain, common mode rejection ratio. So hopefully, again, after the about 2 weeks we spent on this chapter, that those words make more sense to you than they did initially. And then, right, we also talked about the Miller inverting integrating amplifier. And specifically, we went through that whole Laplace example where we calculated the transient response to an input that was provided to us. And then the last bullet here just says that we spent some time talking about the non-ideal characteristics of an op amp.